Thank you for the opportunity to speak at the Scaling Biochar Forum. I'm going to speak about biochar's role in the green economy and its potential for climate change mitigation. It is very well documented the high correlation between human activities and climate change. Most of these activities release greenhouse gases into the atmosphere, including carbon dioxide, methane, and nitrous oxide. All of them contribute to the increase of temperatures on Earth and driving modifications on temperature and precipitation patterns. Carbon relates to this because it's one of the most common elements in the universe. It is the fourth most abundant element by mass on Earth, and for example, is the second most abundant element by mass in the human body after oxygen. Its abundance, carbon-based organic compounds, and its polymers make it the chemical foundation of all life as it is known. When a carbon atom combines with two oxygen atoms makes carbon dioxide, which is one of the greenhouse gases causing warming on Earth. The work of many scientists on the Intergovernmental Panel for Climate Change reports indicate that since 1750, greenhouse gases emissions have increased in specific carbon dioxide from less than 280 parts per million before the Industrial Revolution up to more than 400 parts per million currently. This shows that humans can influence the carbon cycle, which is the movement of carbon between the Earth and the atmosphere that controls the concentration of carbon in the air, and it is the main influence in changes in carbon global stock. Global carbon stock is integrated by carbon storage in different reservoirs on Earth. As we can see here, according to the National Research Council, the biggest reservoir of carbon, not taking into consideration the continental crust, is the ocean. In this slide, also, I don't take into consideration the intermediate and the deep carbon, followed by soil and vegetation, permafrost, the atmosphere, industrial emissions, and land use change. This chart is to indicate the different movements of carbon when entering or leaving on stock, which are known as fluxes. The period that takes between fluxes is called turnover. Also, these turnovers depends on the kind of stock, the period that they remain on it, and they are kind of small compared with the size of the stock, but small changes can create large emissions into the atmosphere affecting climate change. For example, according to NOAA, from 2000 to 2018, carbon emissions to the atmosphere from burning of fossil fuels rose from 6.7 billion metric tons to 10.2 billion metric tons, an increase of almost 4 billion metric tons. So as I can show you here, these are sinking and these are emissions. This makes different kind of movements and fluxes, giving us between Earth and oceans sink of capture of carbon of almost 50% of the carbon emissions for use of fossil fuels per year. With this, if we don't have these sinks, we will be doubling or emissions into air, for example. Carbon Tracker, it's one of the main tools that NOAA has to track the flux of carbon emissions and see how these patterns influence the movement of air and temperature on air, affecting different weather patterns and giving us different kind of influences in climate behavior. And this is what drives climate change. In the long term, this warming of temperatures and changing precipitation patterns are causing different kind of catastrophic disturbances, as we have been looking mostly this year, for example, in the west coast of the United States with the big line, big wildland fires and the floodings that we have had in southeastern United States because of the hurricanes. So when this happened, what we know is that there are catastrophic and not catastrophic disturbances. A disturbance, when we speak in relationship with vegetation, we know that they are disturbances that can create a new age class of trees, a new generation. And depending on the intensity or frequency of these disturbances is how the dynamics of vegetation is going to be affected. Catastrophic disturbances are those that cover big geographical areas, and they have the equivalent of a pandemic behavior, like we are living right now with COVID. This can be man-made, like fire or grazing, or they can be of natural occurrence, like earthquakes, fires, snowstorms, hurricanes, tornadoes, insects and disease attacks, floodings, or not catastrophic, which is regional in area of coverage, and they almost have the same pattern as natural and man-made. As we can see, the effects of the changing of temperature and precipitation patterns have brought drought in different parts of the world, especially in the west coast of the United States. And what happens when we don't have enough water? The competition for water in stand structures starts. This creates imbalances in the ecosystem. Trees that don't get enough water get weak and they are susceptible to the attack of insects and diseases, creating high mortality rates. And then when we have these mortality rates and these imbalances and decrease of temperature, we have high susceptibility for severe wildland fires, as we have been looking into lately. So this is a result of stress in forests. Other factors affecting tree growth and forest stand growth are the tree species intrinsic characteristics like tolerance, genetic pool, and environmental conditions related to weather, like precipitation, solar radiation, daylight temperature, wind, and others. Orography, topography, altitude, and aspect, and soil properties. For example, at sea level, we find out higher biodiversity of species, longer dates, more light, better quality of oxygen. As we go up in altitude, these conditions change, giving us lower temperature, the dates with a lower amount of light, less precipitation, and so on. So this makes more difficult for forest stands to grow, and we have found that less number of species adapted to that kind of adverse growing conditions. Dynamics is influence. But also at the same time, we know that trees fix carbon through photosynthesis and they release carbon through respiration. But in the whole cycle of life of forests and trees, we accumulate organic matter in the topsoil, dead wood, and also with the life cycle of this decomposition of organic matter will be releases of carbon. But at the same time, also this organic matter will promote uh, microorganisms and it will increase the carbon content of the soils. We have studied in the United States the behavior of carbon at above ground, soil level, and below soil. And we know the distribution of carbon in the east, in the west, and in some parts in the middle of the country. The behavior of carbon accumulation in forests is equivalent to a sigmoidal curve, which shows you that as long as the tree is growing, it will accumulate volume, which is an indicator of carbon. And it will reach an optimal point of growing and accumulation, and then as any biological event will start to have a constant accumulation and then a decline, depending on the life cycle and the turn of biological event, lifetime of that species. When we harvest a forest, we harvest some part and we will take some of that carbon. But we won't affect the carbon that is below soil. We will have some carbon emissions given the harvesting process. We will also emit emissions because of the energy used in that process. And we will continue having carbon accumulated in the forest stand depending on the type of silvicultural intervention that we are doing. When we study the effects of climate change and emissions and sinks in the whole system of the forests of the United States, we can see that the behavior of the carbon storage has been almost been constant during the last 10 years, for example. Forests capture between 11 to 13% of total carbon emissions by fossil fuels per year of the United States. And also another sink are urban forests. All other economic activities are creating emissions. So we can see that forests are good sinks of carbon. And they are the best and cheapest way to store carbon on Earth. But also, we can reduce carbon emissions when we use renewable energy in some ways like a wind, hydroelectric, geothermal, or biomass. Biomass for energy production has been increasing lately in the United States. So since I have been following this since 2009 up to now, it came from 7 to almost 12% of energy produced by renewable energy, and increase of biomass in 15% more or less. The United States has 77.5% of the world forest, a little bit more than 300 million hectares, or the equivalent of 753 million acres. We have 10% of the world's timber inventory, which is a lot of carbon in forests. And we only harvest 11 million acres per year. It's around 2% of the total forest area of the United States. So we continue. That's why we continue having a lot of carbon storage in our forest lands. But we can do more to increase carbon sequestration and reduce emissions through forestry, using afforestation, land reclamation, forest restoration, improve forest management, increasing short rotation biomass energy plantations, substitute wood for other materials, increase forest preservation, avoiding deforestation, intensifying agroforestry, and promoting urban forestry. How this relates to biochar and the green economy. The green economy promotes the use of aquatic and terrestrial biomass in producing renewable energy, decreasing the footprint of carbon emissions and creating jobs. When we do forest management, usually we have something that is sometimes called waste, but it's not waste. It's forest residues from harvest that are accumulated and are limbs, branches, and tips of trees, and small diameter trees with low quality. They are placed in slash piles, and sometimes they are left in place, creating some kind of raw material for wildland fires. And one of the main uses to the different innovations that scientists are finding for this kind of materials are, for example, cross-laminated timber, nanotechnology products, and also biochar is one of them. Biochar has the potential that can be produced on site using portable kilns, like in this case, or the materials can be transported to a mill where both of them are produced through the use of pyrolysis in absence of oxygen, producing at the same time biochar, releasing bio-oils, and producing energy. And that energy can be used for heat and cooling systems or can be fed to a small city depending on the size of the production site. The other products coming from the different logs can be transported to different mills and can be used for different purposes, like poles for energy, uh, products for construction, or for furniture, leaving well distributed trees that are not competing for growing space, for nutrients, for water. They can have more advantage of taking light into increasing photosynthesis and sinking more carbon and creating all these different opportunities to increase uh, rural communities' well-being in economic terms, but at the same time decreasing the risk of wildland fires. This is the big opportunity for us. And this relates to climate change and the life cycle of carbon in different ways. As we can see from Dr. Lal, the global carbon budget is placed here through the weathering, sinking carbon, erosion creates some emissions. Net primary productivity is the increase of carbon through photosynthesis and biochar, increase retention of carbon. Soil respiration give us some emissions, and land use conversion also give us emissions. And this goes into land and oceans. The big opportunity has been studied for biochar and carbon sequestration by many authors. One of them is Dr. Lehman. I think he has spoken at this forum too. The importance of biochar and carbon sequestration to mitigate climate change is really real. As we know from several of our ancestors in America use shifting agriculture, which was clear cutting and then burning or slash and burn system for sowing the land. For example, in the Amazon, they created the terra preta. In Peru was the same, in Venezuela, and in Central America, the Mayans did the same thing. They did this because when they slash and burn the vegetation, they increase charcoal content. Mostly this is because in tropical forests, soil productivity is not too high and it leaches very fast. So they have this shift in agriculture in periods of 5 years after burning. They have good crops, and then they have to leave that place, move to the following place in rotation of 5 years, and coming back after a resting period to the same plot of 20 years. So this has created a high amount of contents of charcoal on soils that we can see for thousands of years because of the recalcitrance of biochar and maintaining carbon in place. Dr. Lehman and others have indicated that 12% of the total anthropogenic carbon emissions by land use change can be offset annually in soil if we replace slash and burn by slash and char. Also, agriculture and forestry waste, as I was telling you, and crop residues or different kind of feedstocks can also be used as biochar and decrease also carbon. The use of biochar production, biofuel production using modern biomass systems for conversion can increase biochar and also can increase carbon sequestration and at the same time decrease carbon emissions by using renewable energy. So there is a lot of potential in using these conversion systems, biochar, into different purposes. This can be also increased by use of different carbon trade exchange opportunities, providing more investments in forest management for carbon sequestration, the use of renewable energy to produce and decrease gas emissions, and increase carbon sequestration through the whole system. This is coming and it will come. Finally, forest management gives us a lot of benefits in the United States. It provides jobs, income, taxes, movement of money that will increase if we use different technologies to increase forest management and innovations. The main benefits of all this is that we will have mitigation and adaptation of forests to climate change. We will continue having the ecosystem services that we enjoy, and we will have sustainable forests for the future generations, creating economic opportunities through the whole chain of work of the whole system. And that's what mostly I wanted to talk to you today. I can see that forest management and silviculture are the best approach to healthy, resilient forests, creating opportunities for everybody. Thank you so much for this opportunity.